everyone. Today we're going to extend grammars and grammar fuzzing a bit further, namely by adding a feature that actually overcomes all the limitations of grammar-based fuzzing at once. Now, you may have noticed already when you're dealing with grammars that grammars can be limited in their expressiveness. They're super versatile, they can be used for parsing, they can be used for producing, but there's a couple of things that are difficult to do with a grammar. For instance, if you want to do something like generate a prime number, compute a checksum, make sure that the length element in some binary input corresponds to the length of the string that actually follows afterwards. These things are difficult to do in context-free grammars, if not straight impossible, because, well, this is because of their nature of being context-free. If you look into the field of formal languages, you will know that at the bottom there's the class of regular languages, which is what we commonly see as regular expressions. These are pretty limited. Grammars, context-free grammars to be precise, go a bit further and are super versatile. In my view, they represent the sweet spot in dealing with what is actually useful and what is still very manageable. And above that, you have more classes of grammars. You have context-sensitive grammars and universal grammars. Universal grammars are great because you can do anything that you can do with them. Anything you can also do with a full-fledged programming language. On the other hand, if you want this kind of expressiveness, you may just as well use your favorite programming language right away. So what we're looking into today is ways to combine the best of two worlds, namely to use context-free grammars for still very efficient and predictable and decidable grammar fuzzing. Yet we want to be able to attach particular functions to them, functions that can act as generators and filters and that can be programmed through regular Python code. And for this, we have introduced a special class which is called Generator Grammar Fuzzer, and I'd like to show you how this works right in action. So we go back to one of our regular grammars here, which is our regular break expression grammar, which we have seen a couple of times. So here it comes. So you've seen this already. I don't want to go too much into details here. And yes, you can go and instantiate that and then create arbitrary expressions out of that grammar. But what if, say, we want to have we want to make sure that the numbers we produce have a certain characteristic, say they are all odd or all even or within a specific range of numbers, or who knows, maybe prime numbers, okay? And expressing these properties in a context-free grammar very quickly becomes super difficult. Well, if they should be odd, well, maybe you can restrict the last digit, that's still fine. If you want them to be in a particular range, you can limit the number of digits for the integer that you're producing. But already if you want your number to be divisible by 3, for instance, no chance. Well, when I say no chance, there actually might be a chance, but it becomes super hard to express these properties in a context-free grammar. So what are we doing here? What we do here is we attach specific functions that do the job for us and that generate specific parts of our input, not necessarily the entire input, but only parts of the input, individual elements according to the properties that we'd like to have. So let me introduce a simple function here, which I call my number. This is a function which simply returns a number in the range that I wanted. Say I want numbers to be produced in the range of 100 to 200. So let's see whether this thing works, my number. So let's just invoke it to see whether things work. No, it doesn't. Haha, see, it's too early in the morning. So What have we done wrong here? Of course, there has to be a return in here. Come on, this is Python. Okay, and every time we invoke my number, we get the appropriate number in here. See, this is why we do testing. Okay, good. So far, so good. And now we want to attach this number to our grammar. Now, and the way we do this is again using our ops expansion way. What we do is we say, okay, here's a particular element in our grammar for which we don't want to go through the regular grammar production, that is the integer expands into digits and more digit, but instead we attach a particular function to it, namely the function myNumber, which we have just defined. So what I can do here is you invoke our ops mechanism to add a particular feature that we want to add, and I'm going to add a function that will be called before expansion, or actually instead of expansion. So I'm saying here, so before you go and expand this, dear fuzzer, please go and instead of expanding this, simply invoke this function myNumber, which then will produce a number instead of us producing this integer. So here we go, and if I have done that, what's happening? Nothing is going to happen because I need a special fuzzer to actually take care of this. And this fuzzer is our, sorry, what did I just do wrong? So let's back again. This was interesting. What was that? Okay, and this fuzzer that we're looking at is the generator grammar generator grammar fuzzer. Here we go, and that's great. And again, I pass it the expression grammar, and this generator grammar fuzzer actually picks up this pre-expansion and makes use of it. So if I do this now, and I now invoke gg.fuzz, which is our generator grammar fuzzer, what I get is, well, this is not very exciting. Let's do this again. Here we go. What I now get is an output in which every single integer, if there is one, actually comes from my function myNumber. We can look through that. And here we have an integer. This actually is between 100 and 200. This number here is not between 100 and 200. Why is that? Well, because it's not an integer, it's a float. And if you look closely into our grammar, the float over here is actually not, will actually not be replaced by our own function myNumber. So this is still subject to the same grammar expansion rules as we've seen before. But every other integer in here is still invoked by myNumber. And now if I have, say, I can also do something rather simplistic here. I can also simply return the number 1, 2, 3, 4, for instance. Here we go. And if I then go and fuzz, then what's going on here? Return 1, 2, 3, 4, GG fuzz. Oh, this doesn't work. Why is that the case? Still goes, oh, maybe, oh yes, of course. I also have to add this to our grammars because otherwise it's going to pick up the old definition of myNumber, and no, still not. Oh yes, we also have to do this and that. And now we have it. Thank you so much. Jupyter notebooks are always so fun because of course I have to make sure that this definition of myNumber propagates through the expression grammar and then propagates into the generator grammar fuzzer and then finally gets in here. And here you can see that now that every integer actually also now has the number 1, 2, 3, 4. Well, 1, 2, 3, 4 may not be the wisest of all choices, but the thing is, if you have some whatever function that produces inputs or input elements that are of specific value to you, then you can make use of the generator grammar fuzzer and simply attach these. Now there is a couple of interesting features with generator grammar fuzzer. Instead of pre, there's also the option post, and this is a function which acts as a filter after expansion has been applied. So you can first use the grammar fuzzer to expand something, and then use the post function as a filter to see whether this matches your requirements. This is helpful if the requirement you're having is something that is easier to check rather than to produce. And there are also options to combine all this, of course, and you can even go and create a subclass out of both the generator grammar fuzzer and the probabilistic grammar fuzzer, and then you can actually combine both as you like. So you can have producers being invoked with a certain probability. Everything comes at your leisure. So I very much encourage you to take a look into the rest of the chapter, how these individual generators are being tied into the grammar. There's a bit of deep Python hacking in there. In particular, the filter and production functions have many ways to control the expansion by returning different types. And this gives you lots of control over what is being produced. And the nice thing about all of this is you can still keep the original grammar for parsing, for instance. And when it's parsing, it's going to ignore the generator functions. And in doubt, even if generation fails, the grammar can still be used to produce inputs that at least are syntactically valid. With this, I'd like to invite you to have a look at the many possibilities of generator-based fuzzing. Obviously, since these generators are Turing complete, you can compute anything with them. But the sweet spot is here to actually combine the elegance and versatility of grammar-based fuzzing with small doses of Turing completeness, of Turing complete functions, in order to keep the declarative nature of grammars as long as possible without going into without having to go into lines and lines of code that is then super specific for one particular domain. This is all we're having for today. Enjoy the beauty of generator-based grammar fuzzing. Thank you.